Good morning, everybody. If you recall, late last week we were talking about Hess's law. Okay, I know it's been a few days and a whole weekend since then. Who can tell me something they remember from some of the video notes we looked at on Hess's law, like either what it dealt with or maybe some of the symbols involved? What do you remember?
Delta.
Delta. There was definitely a delta in there. Do you remember the letter after the delta?
Sigma.
Well, there was a sigma. Say again, Haven.
H.
There's an H. Delta H. Remember what the delta H stood for? Big word that starts with an E.
Enthalpy.
Say again, Rain.
Enthalpy.
Enthalpy. Groovy. We talked about delta H and we talked about enthalpy. I would. So enthalpy, if you remember, has to do with how much heat energy there is in a chemical reaction, or in the reactants and products of a chemical reaction. The Greek letter delta, anytime you see a delta, who remembers what that tells you? Change, exactly. So what we're looking at here is we're looking at the change in enthalpy, or the change in heat energy from before and after a chemical reaction. We're just looking for the difference. Now, depending on where the heat moves, you're either going to end up with a positive delta H or a negative delta H when you have a chemical reaction. And we give two words to those, exothermic and endothermic. Who can tell me what one of those two words means? Exo means exit. Good. Which means that the heat energy is leaving. It's being released during that chemical reaction. Excellent. So then endothermic would be just the opposite, right? Right. Endo, think into or enter. It means the heat energy is being taken in. All right? Very good. So when we talked about Hess's law, one of the ways that we can determine the change in heat energy, the change in enthalpy, is by using what's called the delta HF, or the enthalpy of formation. That simply tells us how much energy is either gained or lost when you make 1 mole of whatever substance it is that you're talking about. And this is not something that you're probably going to have to ever calculate. This is something that you can go Google and you can find a table of enthalpies of formation. They stick them in chemistry textbooks. Okay, it's just common knowledge. It's reference. Some of the problems we're going to look at today, they will just give those to you as part of the problem. On other ones, you're going to need to look at the table and look them up yourself. But that in and of itself is not difficult. And so if we're using enthalpies of formation to determine the delta H of a given chemical reaction, we're going to plug it into a big, fairly complicated looking math equation. It's really not that complicated once you know what you're looking at. You all recall this right here. Okay? If it looks like Greek, that's because some of it is. But that's okay. We talked about the Greek letter delta. It's a lot like our letter D, just pointier. And there's the Greek letter sigma. Who remembers what the sigma means? Anybody anywhere? It's been a few days. If I see a sigma, it means I'm taking the sum of something. I'm adding things together. So if I can translate this for you, the delta H of the reaction, and RXN is just shorthand for reaction because chemists are lazy and bad spellers, is equal to the sum of all of the delta H of formations of the products minus the sum of all the delta H of formations of the reactants. Now, I've got a lowercase letter n in there. Does anybody remember from the other day what that letter n is for? It's the number of something. There it is right there. The number of moles. You're going to need a balanced chemical reaction in order to make heads or tails of this kind of thing. So it's important to always check and make sure that if you're given a chemical reaction, you make sure that it is balanced. Most of these that you're going to be looking at will be, but it's always safe to double check for yourself. And we're going to be looking at several sample problems here. I'm going to have a few that I'm going to be doing up here on the wall, so you don't really need to write these down. For two reasons. One, because after we do a few of these up on the board, I'm going to give you a paper, and you're going to have some opportunity to practice a few on your own. But also, I'm going to stick this on Google Classroom, so you can always go back and rewatch the video, and turn the sound off because you hate the sound of my voice, and just like watch it and fast forward and copy it off there later if you want to. Okay? So, are we good so far? Does anyone have any questions? Okay. Sigma means the sum. It means you're adding things together. Good question. Anybody else? Actually, you know what? I'll add that little thing here because that's a good thing to know. Thank you, Jake. Okay, so let's take a look at a fairly typical Hess's law problem, like this one here. Okay, so we've got an equation up here at the top. 4NH3 plus 7O2 yields 4NO2 plus 6H2O. And the G in each one of those simply means that each one of them is a what? A gas. Very good. Okay. So does anybody remember what NH3 is? Off the top of your head? Ammonia. Good job. Okay. So in other words, in these terms, we're taking ammonia, we're combining it with oxygen, we're making nitrogen dioxide and water vapor, right? Now, if I was to ask you what kind of reaction this is, which kind do you think this is closest to? It looks like a combustion reaction, right? Even though we're not getting CO2 and H2O, oxygen is combining with both the nitrogen and the hydrogen, so it's very, very similar to combustion. Okay, in fact, I would consider this, a decent example of combustion reaction. Now, what they give us down here are the delta H of formations of these three substances, of ammonia, of nitrogen dioxide, and water. So what we're going to do is we're going to, flashback real quick, we're going to start by finding the sum of the delta H's of our products. So products, are they on the left-hand side or the right-hand side? Right hand. Products are what gets produced. So the products are over here. So what I'm going to do is I'm going to find the delta H for NO2, gas. It's 33.2 kilojoules per mole. So I'm going to take that 33.2. I'm going to look at my reaction, and I've got 4 moles in the balanced reaction. So I'm going to take that times 4. Okay? Don't start plugging numbers just yet. We're not there. Now I'm going to look for water. Water is a gas. It's negative 241.82 kilojoules per mole. Yes, times 6. Very good, because there's 6 of them in the reaction. Now again, the negative means that energy is being given off. The positive means energy has to be fed in order to produce that. But when I take my calculator and I plug all of that in, and I would like a few of you to take your calculators and plug all of that in so that we can get some confirmation. 1,318.4. Okay, somebody confirm? Negative. Negative 1318.4? 0.12? Negative 1318.12? Okay, I am taking your word for that, and I'm still not writing it down there. 0.12. Okay, so that is the sum of the delta H's for our products. Any questions so far? Okay, now going back to our formula. Now we're going to find the sum of the delta H's for our reactants. So reactants are over here on the left-hand side. These guys here. So I need to find NH3 gas, and I've got 4 of them, so it's going to be 4 times negative 45.9 plus 7 oxygen, so it's going to be 7 times, but wait a minute, oxygen's not in my table here. Yeah, that does suck, right? Now wait, 16 is the molar mass.
Look it up.
No, you don't have to. Oxygen is an element, right? What do you remember about elements from your day? Do I make elements?
No.
They just are, right? So is there going to be any energy being fed in or given off when you make an element? Because you don't. So what number am I going to use? Okay. And 7 times 0, of course, is 0, so we can ignore that. So what's 4 times negative 45.9? Negative 183.6?
Yes.
Gravy. Cool. Now, so we've got products, we've got reactants. Go back to our formula. So we're going to take our sum of our products minus the sum of our reactants. Now, there's 2 places where you can make a mistake here. And I see this all the time. One of them is people forget, okay, well now, what number minus what? Is it this way or that way? It's products minus reactants. It's final minus initial, or minus what you start with. Okay, so if I rewrite this, it's going to be negative 1318.12 minus negative 183.6. Now the other place where people make mistakes on this goes way back to algebra. When you're adding or subtracting negative numbers. If I'm subtracting a negative, what is that just like? Adding a positive, right? So I should end up, if I'm common sensing this, with a negative answer, because this is way bigger negative, but it's going to be less than negative 13 something. It's going to be like maybe negative 1100 something, right? So crunch this and tell me what do you get.
Negative 1134.
Okay, so confirm negative 1134 point what?
5.2.
1134.52. Now, 2 more things we need to look at here before we move on. One, what's our unit? We're talking about heat energy. What is our unit for heat energy here? Kilojoules. Great. So kJ. I don't have to do kilojoules per mole because when I was doing all this, I was putting in molar quantity. So that gets rid of the mole part for my unit. I'm left with just the kilojoules. Second question. This is a negative number. So what does that tell you about this reaction? It gives off heat. Excellent. So what's the word for that? Exothermic. Good job. Question wasn't specifically asking for that one, but what that tells me is if I burn ammonia, it's going to give off heat. Okay? In fact, it's going to give off that much heat for this reaction. This is a really good place for questions if you are feeling in any way, shape, or form lost. Okay? Let's do a finger vote. 0 to 5. How do you personally feel about this? How much your fingers like? 3, 5, 4, 4. Somebody's poking me off. Okay, great. Let's move on. There we go. No kidding. All right. So that's one kind of Hess's law problem. Let me tell you about the other kind. Now, the other kind, you're either really going to love or you're really not going to. Okay? And all of that has to do with how much you enjoy working jigsaw puzzles. Who in here likes jigsaw puzzles? Okay? 2 people. Everybody else is like, I hate that. Except when I'm at grandma's house and I got to do it with her because she's grandma and I got to be nice. So who in here would say at some point in your life you have worked on a jigsaw puzzle? Anybody? There's a few more hands. Good. So we've got some common ground to talk here. When you work a jigsaw puzzle, how do you know what the puzzle's supposed to look like when you're done?
You look at the box.
You look at the picture on the box, right? Good. Second thing, if you look at the picture on the box and you find a piece and you're like, hey, that looks like it goes up there, but you put it up there and you're like, wait, it doesn't quite fit this hole here. What are some things you can try doing with that piece to see if you can make it fit? Try rotating it. Try turning it to see if you can get it in that particular space. If you can do those kind of skills and a little bit of adding and subtracting, maybe some multiplying, then you can do the second kind of Hess's law problem, which is this right here. Now, it's really not a big deal, and I'm going to prove it to you. So it wants me to calculate the enthalpy for this process. Looks like we've got some mercury 1 fluoride. Is what's happening to it? What kind of reaction? Decomposition. Very good. It's falling apart. into mercury and chlorine. Okay? So now here it's not giving me a table of delta HF values. Instead, what it's giving me is it's giving me two other reactions and telling me what the delta H is for those reactions. Hess's law is all about finding the difference in enthalpy from where you start to where you end up. It doesn't matter what pathway you take to get there. The only things that are important is starting point and ending point. So we can look at this like we look at pieces in a jigsaw puzzle. This up here at the top, this is our picture on the box. Okay? So that's where all the pieces need to go. Now this down here, these are our jigsaw puzzle pieces. So I'm looking at the box. Where do I see Hg2Cl2? Do you see it down here anywhere? Where's it at? It's on the second one right there. Everybody see that? Okay. Now do all the little subscript numbers and things matter here? Oh yeah, like crazy they do, because look right there. That's almost the same thing, but it's not, right? So you have to be really careful you're finding the right puzzle piece. How about just Hg, just aluminum? Aluminum. Mercury. Both of them? Yeah. It's right there, and it's right there. You guys see that? What does the L mean?
Liquid.
Liquid, great. Okay. What about chlorine gas, Cl2? It's on the top one. Great. So, we have identified that, yes, these are the puzzle pieces that will fit our puzzle. Now, what we need to do is we need to check and see if they're going to fit in there just like they are, if we're going to have to turn them a little bit to make them fit. And here's what I mean by that. You look at each of these, look the reactant side and the product side. In order to fit, it's got to be lined up the same direction that it's lined up there. So look at our Hg2Cl2. It's in the reactant side right there. Is it in the reactant side down here? No, it's in the product side. So to make this fit, what we actually have to do is take this entire thing and rotate the puzzle piece. So we're going to take this whole thing, we're going to flip it around, and when I flip this thing around, here's what it's going to look like. It's going to look like Hg2, Cl2, solid, yields mercury, liquid, not a C, but whatever, plus HgCl2 solid. Okay, y'all agree? All I did is turn it around. Now, think about what this number right here means. This number right here means that that reaction releases 41.2 kilojoules of heat. If I flip it around backwards, what do you think happens to that number?
Turn positive.
It's going to turn positive because instead of the heat being released, heat's going to be absorbed. So I take this number here and I turn it into a positive when I flip it around. Make sense? Okay. Well, let's look at our other pieces here. Looks like Hg's everywhere, so let's leave that alone. Let's go look at our Cl2. Our Cl2, it's in the product side in our puzzle up there. Is it in the product side here? It is not. So what are we going to have to do with this piece up here? We're going to have to flip it around too, right? So when I flip it around, let me bring it down here. And it's going to be HgCl2 solid. Where'd that green one come from? That's weird. Did I do that? Huh. Trippy. Yields Hg liquid plus Cl2 gas. And again, because I flipped this around, that was a negative number, it becomes a positive. Okay? Now, let me show you what's really cool about this. We're going to take both of these and we're going to stick them together in one big reaction, which means that these right here, that means that on the left-hand side, we've got these guys here. On the right-hand side, we've got these guys here. Now, do you see anything doubled up anywhere on the same side of the reaction?
The top one, the red one. Hg.
Yeah, look, I got liquid Hg and I got liquid Hg. So when I put those together, guess what I'm going to have? Exactly. Have 2 Hg liquid. Okay? Is there anything that appears on both the reactant side and the product side? HgCl2 is on both? Yeah, totally. This one here? and this one here. So if they're on the same side, I get to combine them. If they're on opposite sides, guess what I get to do? Knock them out, cancel them. So that cancels that. And look at what I'm left with. Okay, he's going to come down here, so plus Cl2 gas. He's going to come down here. So on this side, I've got Hg2, Cl2 solid. Now, take a look at my picture on my box up there. It's the same thing. Why do I keep crossing my L's? That's weird.
Quite cool.
Okay, that is cool. Now, that's not the main point, though. The main point, though, is we're also going to do the same thing with these delta H values for each reaction. We already made them positive. Now what we're going to do is we're going to add them up. So we're going to do 224, positive 224, plus positive 41.2. 265.2 kilojoules. Okay. Positive, right?
Yes.
Which means is energy being given off or taken in? Taken in. So this process up here is endothermic. It's absorbing that much energy. Now, I'm not going to lie. That's a lot to chew on, and I'm hoping there's some questions out there. So who has a question about any part of what we just did? Shoot.
What are we exactly trying to
We are trying to find how much heat energy this reaction up here gives us. We don't know that to start with. We do know how much there is for these other two. So we're just taking the info from these other two, cramming them together to find out how much just this one does. It gets a little more complicated sometimes, but not much.
So why wouldn't we just make those two positives out?
Well, we don't know that they're positive until we analyze this, and we see if we need to flip them around. You're not always just automatically going to change the signs and add stuff together. Sometimes you leave them alone. Sometimes you might even like double or triple how much is there. And we'll look at some more examples on how that works. Okay?
What's the point of making the bottom?
The point of making the bottom is just kind of checking to see that the top makes sense. Hey, now I like where you're going with that, because once you know that the bottom should make sense, you can kind of safely not worry about this part and just worry about how it changes the numbers. And it's a lot faster. Yes, sir?
How do you know when you're supposed to, like, if and when you're supposed to flip them?
Okay. If and when you're supposed to flip them, you look to see what side of the reaction. See how this one here is on my reactant side, but down here is on my product side? That's why I had to flip that around to get him over here. Okay. Anybody else? Good questions. Let's look at a couple more practice problems. This one's like the first one we did. We're given some delta H's of formation here. So you tell me, how do I work this? What do I start with?
Products.
Products, right? They're the ones on the right side, correct? So I'm start with my products. Okay, so what do I need to know from that?
That Al2O3 is negative 16.
Okay, and I've just got one of them, right? Because there's not a coefficient there. So it's going to be negative 1676.
Plus 0.
Okay, plus 0. 0 because iron is an element, right? Actually, let's not get in a rush here. It's plus 2 times 0. Right? Okay. All right, good. So, gee, let's do this math. What's negative 1676 plus 0?
Negative 1676.
Awesome. Okay, cool. That's our product. Now what?
A reactant.
Fe2O3.
Okay. What about aluminum?
So it's going to be 2 times 0.
2 times 0. Because aluminum's an element, so it's 0. Plus?
Negative 824.2.
Okay. And again, there's just one of those because there's an understood one there, right? Negative 824.2. So 0 plus negative 824.2?
824.2.
Negative 824.2. All right. So now, going back to my original equation, remember I take products minus reactants. So what minus what here?
Negative 1676 minus negative 824.2.
Okay. So if you y'all crunch that? Tell me what you
Negative
get.
851.8.
Wow, that's quick. Super speedy. Negative 851.8. Okay, kilojoules. Now, let's common sense this and make sure it makes sense before we move on here. We've got a negative being subtracted from a negative, which is like adding a positive, and so this big number we start with is going to get smaller negative, right? So about half of that's going to be about 800 something. So yeah, totally makes sense. What else can you tell me about that reaction?
It's a double or single replacement.
You're both right. It is single replacement. Good job. And it is exothermic. Because that's negative, so it's giving positive. Good. That's exactly right. Yes. Okay. Good deal. So, can we establish that that kind of problem is a little bit quicker and easier than the other kind? Okay. All right. Let's look at another one of the other kind. All right. We got a puzzle box. We got pieces. So let's first of all find our pieces. Okay. Where do you see zinc? On the top. Okay. What about sulfur? Uh-huh. Okay. What about O2 gas?
On the bottom.
Cool. See why I had you get the colored pencils? What about ZnSO4?
On the bottom.
On the bottom. So let's see what we need to do with our pieces. Starting with our zinc. Our zinc and our sulfur are both on the product side here. Are they in the correct place?
No.
They are not. So what are we going to have to do with this top one?
Flip it.
We're going to have to flip it around, right? So when we flip it around, what does that do to our sign here?
It makes it negative.
It makes it negative. Good deal. What about our oxygen? Is it on the correct side?
Yes.
It is. But what's the problem?
Not enough of that.
There's not enough. You see how down here there's just one, and up here on the box there's two of them? So how are we going to fix that? I'm not going to add, I am going to multiply. Now, the way I'm going to multiply, I'm going to take this entire reaction and multiply it times 2, which is going to give me one of those, two of those, and one of those. If I'm doubling the reaction, what do you think happens to my number here? Oh, you guys are so good. We're going to take that times 2. We're going to leave it as a negative, but we're going to take it times 2. Now, at this point, if you have faith in the process, you could just make that a negative, double that, and add them together to get your answer. Okay, and I know Daniel's already there. But, just for argument's sake, let's make sure that's going to make sense, and let's see why that works. Okay, I'm going to rewrite my equations down here. I'm going to start with the first one. I'm going to flip it around backwards, so it's going to be zinc plus sulfur yields ZnS, zinc sulfide. Okay? The bottom one, I'm leaving it in the same direction, but I'm just going to double it. So what's 2 times 1/2?
1.
1. So ZnS plus 2O2 yields, again, 2 times 1/2 is 1, so ZnSO4. With me so far? Is there anything that we can either double up or cancel? ZnS, see how it shows up on the product side and on the reactant side? So look at what we got left over here on our reactant side. Zinc plus sulfur plus 2O2. Look what we got up here. Zinc plus sulfur plus 2O2. The only thing on our product side is this, which is what we got right there. So it checks out. Now let's play with our numbers. So we're going to take negative 206, because we changed directions, we changed the sign. Negative 206 plus, now what is negative 388.4 times 2?
Negative 776.8.
Awesome. So plus negative 776.8. So we're adding two negatives together, so it's going to make a bigger negative answer. So what is our answer?
Negative 982.8.
Somebody confirm?
I got negative 900. I don't
Negative 982.8.
Yeah.
All right, cool. So negative 982.8 kilojoules. And we're done. All right. It really doesn't get much harder than that. Y'all do me a finger vote here, 0 to 5. How are you feeling about this second type of problem, be honest? I'm seeing a lot of 5s out there. And 3s and 4s. Seeing a 2. Now, I was thinking that you were like really getting this beyond this. Why are you voting? Oh, you're going to a 3 there.
Just the switching this thing.
Yeah.
Okay.
I don't like it.
That's fine. I understand. Like I said, you know, it's kind of like working a jigsaw puzzle. If you hate those because you hate lining stuff up and flipping things around, you're probably not going to like this too. But we are going to practice some more and you are going to get better at it. So, I think we probably have time to work one more up here on the board. Would you like to see another one of the first kind? Or would you like to see another one of the second kind? All right. Let's take a look at this one here. Okay? All right. So calculate delta H for the process. Graphite plus hydrogen yields methane. Okay? What kind of reaction is this?
Decomposition.
It's synthesis. We're putting stuff together, not taking it apart. Okay, good. So, find the puzzle pieces. What do you see? I see graphite. Where's he
It's
at?
on the first one.
Cool.
Um,
Do you see H2 anywhere?
the second one.
I see it on the second one. Cool. How about CH4?
The third one.
On the third one. Cool. So let's look at each one of these. Let's start with our carbon, our graphite. Is it on the correct side of the equation?
Yes.
Do I have enough?
Yes.
So do I do anything to this first one?
No.
Nope. That one's good. Okay, how about our second one? H2, is it on the correct side?
No. Yes.
It is actually. It's on the left-hand side of the arrow then.
Oh.
See?
Yes.
I do have to double it because I need 2 of them. So I take this entire thing times 2, which means I take this number right here, times 2. What about the last one?
It's on the wrong side.
It's on the wrong side. It's the right number, it's just in the wrong place. So I'm going to take this last one, flip it around, which means that this negative becomes a positive. Okay? Now, if you would like at this point, we can go ahead and crunch our numbers and see what our answer should be. Let's do that. Let's do negative 393.51 plus, somebody crunch this for me. What's negative 285.83 times 2? 571.66.
Yes.
You all agree?
Yes.
Okay. And then plus a positive 892.
Negative 73.6.
Yes.
Okay, so when you confirm negative 73.17
Yes.
kilojoules. Okay, that should be our answer. Okay? Okay. Now, we can either move on with our lives, or we can confirm real quick that that's going to make sense. Oh, y'all are no fun. Okay. Who'd like to see me? I promise I'll do it fast. Is everybody like, yeah, I'm good? Jake's like, I'm doing it. Cool. Well, I wanted to do it anyway. Thank you, David.
I'll be the black sheep of the group.
Good man. Okay. All right. All right, so first one we leave alone. So on the left-hand side, I'm going to have carbon plus O2. Right-hand side, I'm going to have CO2. This one here, I'm doubling. So 2H2 plus 2 times 1/2, so 1O2 yields 2H2O. On this side, I'm flipping it all around, so CO2 and H2O is on the left, so CO2 plus 2H2O. And then these two here are going to be on the right, so CH4 plus 2O2. Now, what can we cancel? I see a CO2 and a CO2. Cancel those. What else can we get rid of?
And H2O.
2H2O. Cool. What else?
O2 and
Yeah, so I've got O2 and I've got O2, which add up to what? 2O2. So I can cancel those. What am I left with?
carbon.
Carbon and 2 hydrogen.
Carbon and CH4.
And 1 CH4. So yeah, it totally checks out. Questions? Okay, how are y'all feeling about this? Any better? I know it doesn't sound like a trip to the pool or anything, but does it look doable? Better than stoichiometry?
Yes.
All right, we can agree on that. That's good.